Today we're going to talk about the chain rule. You learned about the chain rule back in Calc 1, I guess, and this is the thing, for example, that let you differentiate something like sine of x squared. And you knew that you would take the derivative of the sine, cosine, of x squared, and then you knew that by the chain rule you'd better multiply by 2x, the derivative of what's inside. Well, what's the multivariable version of this? That's the goal today, is to learn the multivariable version of this. And then we're gonna, like we did last time, practice a little bit more implicit differentiation in the multivariable context. So the big idea here is, like in most applications, mathematical models, we might have a model that depends on a collection of variables, say x and y, and those variables themselves might depend on yet another collection of variables, say s and t. And then it's a natural question to ask, well, how does this original variable depend on these other variables way at the end of the chain? So we have this chain of variables, and the chain rules tells us how to compute derivatives with respect to those independent variables at the very end of the chain. So the dependent variable is at one end of the chain, the independent variables are at the other end of the chain, and in between there might be multiple intermediate variables. Chain rule will let us figure out how this dependent variable depends on these independent variables way, sort of connects either ends of the chain. Also in this section, we're going to talk about implicit differentiation. And this, for example, if we focus on this example right here, we see this function 8xyz plus z squared equals sine z. It would be hard to solve for any of these variables in terms of any of the others, although probably you could solve for x and y relatively easily, but it would be really hard to solve for z in terms of x and y, for example. The implicit differentiation will let us sort of declare that z is the dependent variable, x and y are, say, the independent variables, and lead us into how to differentiate that way. But that doesn't mean we always want z to be the dependent variable and x and y to be independent. We could say let x be the independent variable and y and z be the independent variables. Again, implicit differentiation will let us extract derivatives of dependent variables with respect to independent variables. And the big difference here is we've got several variables instead of just two variables, x and y. But partial differentiation, if you keep your wits about you and you follow the rules of just keeping all the independent variables constant except the one that you're differentiating with respect to, you'll land in the same place as you did in Calc 1. Again, not explicitly how we're talking about differentiation in this section, but just a bit of a review. Okay, let's talk a little bit about the textbook here. We want to recall the chain rule from Calc 1 first of all, so that's where the textbook starts. And you'll remember that if we have two functions, f and g, and we take their composition, f of g, the derivative of the composition is f prime of g times g prime of x. That's the rule that you learned back in Calc 1. How does that work in several variables? Well, let's say we have a function f of two variables, x and y, and in turn each of those variables is a function of t, g of t, h of t, then we can take the derivative of z as it depends on t at the other end of the chain by writing this expression. We take the partial of z with respect to x times the partial of x with respect to t plus the partial of z with respect to y times the partial of y with respect to t. This is the core of what we're talking about today. If you can get this in your head, everything else will flow. All right, the proof of this relies on something that we didn't really emphasize from last time, but if you want to write, say, a derivative of z, we know from the last section that we can write it like this. And this beginning part, these first three terms, look a lot like the tangent plane formula. In fact, it is the tangent plane formula. And what makes this the derivative of z is the presence of this, what we would call an error term, e of x and y. And what's special about this error term is as x and y approach x naught and y naught, the point of tangency, this error term goes to 0 in a very special way. This thing goes to 0 even when it's divided by the square root of x minus x naught squared plus y minus y naught squared. So by itself it goes to 0, but it even still goes to 0 when you divide it by this thing that is also going to 0. So this goes to 0 really, really strongly. So strongly that it can survive the fact that this also is going to 0. Okay, so let's see how this leads to the chain rule. If we move z of t naught over to the left-hand side, and let's set up some parameters here. We're assuming that x naught, or that x is a function of t, and y is a function of t, and furthermore that when we plug in t naught, we get x naught, and when we plug in t naught over here, we get y naught. In that notation, we can move this number over to the left-hand side as z of t naught, and what's left behind is the rest of this expression here. And we're going to replace x with x of t and x naught with x of t naught, and so on. And then remember that this error term also goes along for the ride. If we divide both sides by t minus t naught, on the left-hand side we get a difference quotient, which is going to lead to a derivative. And on the right-hand side, we get a pair of difference quotients, here and here. And the error term also gets divided by t minus t naught. Now that's okay, because we're eventually going to take t going to t naught. This is going to go to 0. And what we know is that this thing divided by something that goes to 0 is still going to go to 0. So this is, in the long term, it's going to just go away. As we take t to t naught, this difference quotient is going to go to dz dt, which is the thing that we seek. This is a constant with respect to t, so no changes there, it just goes along for the ride. And what we get here, moving the limit onto this term, is the derivative of x with respect to t. That's this guy. Similarly, the partial of f with respect to y at x naught y naught just carries through, and we get dy dt. This bit here is exactly the chain rule. If you look closely at this and you compare it to this, that's exactly what we see. The question is, what happened to that last term, that term with the capital E in it? Well, because we know by the previous section that such an E exists and that it has these special properties, we can conclude that this piece goes to 0 as t goes to t naught. And that's what this part is discussing. It's kind of going through the work of showing that that part goes to 0. And again, what's left behind is exactly the chain rule for z as a function of x and y both as functions of a single variable t. Just a bit of notation. X and y in this context are called intermediate variables. T is called the independent variable, and z is called the dependent variable. We'll do a lot of examples at the end here, but let's just walk through one here. Let's look at, for example, b. All right, so in b we have this function. Z is a function of two variables, and it's the square root of x squared minus y squared. And in turn, x and y are both functions of t, explicitly given here. If we want to find how z changes with t, we apply the chain rule. And I still do this to this day. I write out the chain rule, dz dx times dx dt plus dz dy, dy dt, and then I start computing all of those things. That's what's going on up here, dz dx, dx dt, dz dy, dx dt. Sorry, that's a typo. That should be dy dt. And we take those and substitute them into this expression. And then you can leave it, lots of people might leave it like this, especially if you're going to go on and do further substitutions. But if this is the endpoint where you're asked for dz dt, then it's kind of incumbent upon you to go ahead and replace all the x's and y's with their corresponding functions of t. That's what's going on here. So then in the end, dz dt is a function solely of t. When in doubt, go ahead and do that process and replace it with a function solely of t. Continuing, we can now lift or up the ante. We can say that z is a function of x and y, and in turn that x and y are functions of u and v. And now instead of getting a derivative of z with respect to t, we have a partial derivative of z with respect to one of these independent variables u or v. But remember that partial differentiation is really just differentiating in one variable and holding the other variable fixed. So in the end, the only difference between this expression and dz dt up above is that we replace dz dt with partial symbols, partial z with respect to u, and we replace dx dt with dx du, the partial of x with respect to u. So this maps directly onto the previous theorem, 4.8. We just have partial symbols. And furthermore, because there are two independent variables, there's the potential for two partial derivatives, one with respect to u, one with respect to v. And so that leads to the second formula. But again, the second formula is no different than what we see in 4.8, where we differentiate with respect to v and we hold u constant. So memorize that formula from theorem 4.8 and then just recognize that it maps directly onto partial derivatives where you're holding all of the variables fixed except one. There's this tree diagram. If it helps you, go ahead and study it and memorize it. I don't use it. I live my life mostly up here with this one formula and then adapt my skills accordingly. The only way that this variable changes substantially in my mind is when z is a function of three variables, you get three terms. You include the derivative with respect to that third variable. And in fact, that's what's going on down here with the generalized chain rule. You might have a function that depends on m variables, and each of those variables depends on n independent variables. You can take the partial with respect to any one of these t variables by writing out the sum in exactly the way that you would expect. W with respect to x1, x1 with respect to tj, and so on. So just make sure that you sort of include all of them. Here's an example using the generalized chain rule. I guess let's walk through it a little bit. We have w as a function of three variables, x, y, and z. And you're asked to find the partial of w with respect to u, for example. So if I want to find the partial with respect to u, I write the partial with respect to x times the partial of x with respect to u, plus w with respect to y, y with respect to u, plus w with respect to z, z with respect to u. And then I just start grinding it out. I start calculating all of those partial derivatives that I need for this expression, and I plug them in. And then if I'm not asked to do any other further substitution, I just make sure that I express w in terms of the independent variables u and v. Great. You can draw the tree diagram if that's your vibe. I'm going to move on to implicit differentiation. One of the things that we can do with implicit differentiation is we can find dy dx in the context of some implicitly defined function y as a function of x. If we have such a function, let's say f of x equals some constant, f of x and y equals some constant 0, we can actually use the chain rule to calculate dy dx. So we take the derivative of f with respect to x. That's the partial of f with respect to x times dx dx, which is 1, plus the partial of f with respect to y times dy dx. This is the thing that we seek. And on the right-hand side, the derivative of 0 with respect to x is just 0. Solving for dy dx yields the formula up here, and this is a quick way of computing dy dx implicitly. It lets you avoid solving for y in terms of x, and it lets you express it in terms of partials of f with respect to x. Let's look at an example of that. So let's say we have this implicit function here. We just always set it equal to 0, and we'll define f as what's on the left-hand side. We calculate the partials of f with respect to x and y respectively. We form this quotient, and we end up with the derivative dy dx. This is an implicit derivative. If you want to find the slope of the tangent line at, say, the point 2,1, you set x equal to 2, y equal to 1 everywhere, and you compute dy dx. All right, let's get into some of these exercises. We'll jump over to the notes and start with exercise 220. So I'm starting with 220 just because I noticed that there was a typo in there, and I wanted to kind of bring it to your attention. For some reason, all this extra gobbledygook is in here, and we don't need it. So I'm going to cross that out. You're given a function f of x and y is equal to x plus y, and you're asked to find the partial of f with respect to theta. So pay attention to which independent variable you're differentiating with respect to, and then write out the formula for that. So the partial of f with respect to theta is the partial of f with respect to x times the partial of x with respect to theta plus the partial of f with respect to y times the partial of y with respect to theta. And you just keep writing out these terms until you've exhausted all of the intermediate variables, and then make sure that you multiply by the derivative of the intermediate variable with respect to the independent variable that you care about, in this case theta. So if this was a function of 3 variables, we'd have 3 terms, each ending with a derivative with respect to theta. Now I need to find all of these various pieces. So the partial of f with respect to x is just 1. The partial of f with respect to y is again 1. I'm just differentiating x plus y with respect to x and y. The partial of x with respect to theta, you go to this expression, x equals r cosine theta, and you take the derivative with respect to theta. You get minus r sine theta. The partial of y with respect to theta, you go to this expression, y equals r sine theta, and you differentiate with respect to theta, r cosine theta. I've got all the pieces that I need. I'm going to substitute them into my chain rule expression. Partial of f with respect to x is 1. Partial of x with respect to theta is minus r cosine theta. Partial of f with respect to y is 1. Partial of y with respect to theta is r cosine theta. Let's clean this up a little bit, and we get, I should be careful here. Partial of x with respect to theta was minus r sine theta. Apologies. All right, there is a common factor of r. We could factor that out. What's left behind is cosine theta minus r sine theta. So if we were wondering how the function f changes with respect to theta, we would answer it changes with respect to theta according to this expression, r times the quantity cosine theta minus r sine theta. Moving on to 229. Slightly different, right? We've got u as a function of x and y, and then x and y are both functions of t, explicit functions of t. And again, keep your eye on the prize. The goal here is to find du dt. So I see that sitting right here. So I write out the chain rule formula for du dt. That's always where I start. That's the partial of u with respect to x times the partial of x with respect to t. I can write partial of x with respect to t, but I see that x is secretly a function of a single variable, so technically I should write dx dt. Partial of u with respect to y times dy dt. So that's the appropriate use of the notation. Once again, I see these four derivatives that I need to calculate. Let's find the partial of u with respect to x. We focus on this expression up here, e to the x sine y. That's what u equals. E to the x sine y. The partial of u with respect to y. Again, back to this expression, e to the x sine y. And we get those two derivatives. The partial of x with respect to t, we focus on this expression, is going to be minus 1 over 2t times the derivative of 2t with respect to t, that's 2, and that simplifies to negative 1 over t. The derivative of y with respect to t, we're going to focus on this expression, y equals pi t, and that's simply pi. We have all the pieces. Let's substitute them into our chain rule expression. The partial of u with respect to x is e to the x sine y times the derivative of x with respect to t. That's minus 1 over mixed expression of x and y and t here, but that's okay. We're going to substitute values for x, y, and t in a moment. Plus the partial of y with u with respect to y, that's e to the x cosine y, times the derivative of y with respect to t, that's pi. Now, we're asked to find du dt when x is equal to the natural log of 2 up here and y is equal to pi over 4. For what value of t does y equal pi over 4? Well, if we look at the expression for y is equal to pi over 2. So the value of t that gives me pi over 4 is 1/4. Now, if this is a carefully constructed problem, you don't have to check this, but it's probably worth checking that when I take t equals 1/4 and I plug it into the expression for x over here, that I get the natural log of 2. So let's check that. Minus the natural log of 2 times 1/4 is minus, let me slide this down a little bit, minus the natural log of 1/2. Remember that that's the same as minus the natural log of 2 to the minus 1. 1/2 is 2 to the minus 1. And then remember that the minus 1 as the exponent in here can come out front and cancel with this minus 1, and we get the natural log of 2. So in fact, when I substitute t equals 1/4 into minus natural log of 2t, I do in fact get the natural log of 2. So this parameter value, t equals 1/4, is what gives us x equals ln of 2, y equals pi over 4. Let's continue the original problem. We've now found that t is equal to 1/4 for these particular x and y values. We have e to the ln of 2 times the sine of pi over 4 times negative 1 over 1/4. That's all of the stuff from the first term, plus e to the ln of 2 cosine of pi over 4 times pi. I think it's incumbent upon you as a studious and careful math student to simplify this as much as possible. E to the natural log of 2, what's that? 2. Sine of pi over 4, what's that? Root 2 over 2. Negative 1 over 1/4, what's that? It's negative 4. And repeating all these simplifications in the second term, we get 2, root 2 over 2, and pi. I think we should continue and simplify again as much as possible. We get a little bit of cancellation here. and here. And what's left behind is negative 4 root 2 plus pi root 2. Oops, pi root 2. There's a common factor of root 2 in both terms, so let's factor that out. And in the end, we're left with pi minus 4. All right, moving right along, 247. All right, in 247, the only real difference here is we've got a function w of 3 variables, so we'll see a chain rule with 3 terms. Once again, always start with writing the formula. Well, actually, I take it back. Always start with figuring out what is being asked for. So in this case, we're looking for the partial of w with respect to t. And what we see here is that each of these terms depends on the variable t. Honestly, technically, this should be dw dt because there's only one independent variable, t. So that's a bit of a typo. So dw dt has a chain rule expansion that looks like this. The partial of w with respect to x times dx dt, partial w with respect to y times dy dt, partial w with respect to z dz dt. So we have a 3-term chain rule, and now we have to fill in all of the various bits. Let's first compute the partial of w with respect to x. Okay, the derivative of sine xyz with respect to x, that's going to be sine xyz times the derivative of xyz with respect to x, which is yz. Clear? And I'm going to take advantage of the symmetry of this situation, the symmetry of this expression, to assume that if I'm taking the derivative of this thing with respect to x, I get this expression where there's no x. If I'm taking the derivative with respect to y, I should get this expression, but instead xz sine xyz. And last, the derivative of w with respect to z should be xy sine xyz. If you're not comfortable taking these shortcuts, by all means, just do the derivative explicitly. Now we need the derivatives of x, y, and z with respect to t, so let's do that. The derivative of x with respect to t is simply negative 3. Of y, oops, pardon me, dx dt, dy dt is going to be minus e to the 1 minus t, and dz dt is going to be 4. Great. All right, putting all of that to work in the expression. I know by the presence of these partial derivatives in each of the 3 terms and by the presence of sine xyz in each of the 3 terms that there's going to be an overall factor of sine xyz in front of this derivative. All right, so I'm just going to get that out of the way at the get-go. Now, in the first term, what's left behind is yz times dx dt. That's negative 3. In the second term, what's left behind is xz times dy dt, minus e to the 1 minus t. And in the third term, what's left behind is xy times the derivative of z with respect to 4. Sorry, with respect to t, which is 4. And we get this expression. Now, we're not doing any further substitution like we did before, and yet we have this mixed expression. We have x's and y's and t's, but if you'll remember, we were asked to find dw dt. A polite mathematician would express the result in terms of solely in terms of t. So how are we going to do that? We're just going to go through and replace everything with, so this is sort of an aside here, a computational aside, and we're going to go through and replace everything with the corresponding expression in t. So x is 1 minus 3t, y is e to the 1 minus t, and z is 4t. So all of that is inside the argument of the sign. And then we're going to go through, let me clean this up. Well, it's not worth it. We're going to take minus 3 times y, which is e to the 1 minus t, times z, which is 4t. And we'll take x, which is 1 minus 3t, times z, which is 4t, times minus e to the 1 minus t. And we'll keep going. We'll take x, which is 1 minus 3t, times y, which is e to the 1 minus t, times z, times 4. And let me just double check that. So here we have y, z, that looks good. Here we have x. Let me just sort of put little notes here. So this is x, and this is y, this is z, this is x, and this is z, and this is x, and this is y. So that's how we're doing the substitutions. And then you could go through and kind of clean this up as much as possible. I'm for the sake of time, I think I'm not, but we do see a common factor of e to the 1 minus t in each of these three terms, which we could pull out, and then we could simplify what's left behind, which is just simple polynomials in t. Okay, I do a lot of calculation when I'm doing these exercises, and I thought it'd be fun to do a more abstract exercise. So in this exercise, we talk about functions that are homogeneous of degree n. This is useful. This comes up in statistics a lot. It comes up in physics a lot. And for us as mathematicians, it's really just this abstract property that if you take a function of x and y, and you replace x and y with tx and ty, we see that we can factor the t out to some power. This is mostly used for scalar multiplication. It tells us how scalars move out of functions like this. And an example of this is the distance, well, the distance function, the magnitude of vectors. The magnitude of a vector, if we pretend that it's a function, so let's say call it n of the vector v, which is the magnitude of the vector v, which is the square root of x squared plus y squared, say for a two-dimensional vector. We can pretend that this is a function of two variables, n of x and y. And if we look at scalar multiplication of a vector, alpha times v, that's the vector alpha times x, alpha times y, like that. And we might ask ourselves, well, how does the variable alpha behave? And we can say that alpha, n alpha of x, alpha of y, is equal to the absolute value of alpha times n of x and y. And you can verify that by just substituting it into the square root. And what you'll get is a factor of alpha coming out. This is homogeneous of degree 1. You might worry a little bit about the absolute values, and I'm not going to get into that right now, but we would say that this function is homogeneous of degree 1. So the norm function is homogeneous of degree 1, the length of a vector. More abstractly, let's look at problem 250. If I look at this thing, what I see is there are three instances of the independent variable xy here and 3 instances of the independent variable here multiplied together, I'm going to guess that we're talking about n equals 3. Let's verify that. F of t x t y is equal to tx quantity squared times ty minus 2 times the quantity ty cubed. If we simplify this, we get 2 factors of t here and a third factor here, so that's t cubed x squared y, and 3 factors of t here, so 2t cubed y cubed here. We have a common factor of t cubed in both, t cubed. What's left behind is x squared y minus y cubed. And if you look at this just the right way, you'll notice that the thing in the parentheses is really just f of x and y. So what we proved is this part of the expression that I've circled in red up above. F of t x t y is equal to t cubed f of x y. Therefore, this is homogeneous of degree 3. Now, this theorem goes on to say, or this exercise goes on to say, that if a function is homogeneous of degree n, then it satisfies this weird expression. And we're asked to verify that it indeed satisfies that weird expression. So let's do that. Let's make a little bit of room down here. How do we verify that an identity is true? We start with one side of the identity and we work our way to the other side of the identity. So to prove the identity in the green bubble, I'm going to start with the left-hand side. X partial of f with respect to x plus y partial of f with respect to y. I know that we can just carry along the x. What's the partial of f with respect to x? Well, that's 2xy. Oops, 2xy minus 0, because the derivative of 2y cubed with respect to x is 0, plus y times the quantity. Now we have the derivative of f with respect to y. That's x squared minus 6y squared, just like that. Let's do some algebra. Doing a bit of algebra, we get 2x squared y plus yx squared minus 6y cubed, like that. Let's combine like terms. So that's 3x squared y minus 6y cubed. Let's factor out a 3. 3x squared y minus 2y cubed. And that last expression should look familiar. That last expression is really just f of x and y. And we started on the left with f times the partial of f with respect to x plus y times the partial of f with respect to y. That was the left-hand side of the green bubble up here. And we ended up with, on the right-hand side, 3 f of x and y. N is equal to 3. It all checks out. And we'll put a green check mark next to that identity. So this function is homogeneous of degree 3. And we've verified that it satisfies this equation for n equals 3. Got it? So when you're proving an identity, you always start with one side and you do algebraic manipulation to end up with the other side, and that's a proof. Let's do an application to circuits. So we've got the total resistance in a circuit is given by this complicated expression up here. XYZ over YZ plus XZ plus XY. This is a thing that can happen in circuits, so this is not an unusual expression. And And then we're given some additional information. We're given that at a particular moment in time, the resistance X is 100, Y is 200, and Z is 300 ohms. And we also know that dx dt is 2 ohms per minute, dy dt is 1 ohm per minute, and dz dt is 0 ohms per minute, no change. So what all of this is telling me is that R is a function of x, y, and z, and x, y, and z are each functions of t. Find the rate of change of the total resistance R with respect to time. What are we looking for? dr dt. Now that we've figured this out, and we know that R is a function of x, y, and z, and those in turn are functions of t, we can write out the chain rule expression for this. Partial of R with respect to x, dx dt, partial of R with respect to y, dy dt, partial of R with respect to z, dz dt. Now, your job, should you choose to accept it, is to compute all of these various quantities. We're not going to be computing these quantities because we're not given them in general. We only have these at a specific time. And what we have for these is that at those specific times, they are 2, 1, and 0 respectively. Okay, I'm going to show you a feature of Sage that I quite like, and you might find useful not only in this class, but if you move on to other sort of applied analysis classes like those you might find in physics or PChem or even in my own engineering math class, which I'll be teaching next semester. It turns out that Sage is able to manipulate abstract functions, and if you take advantage of this, it can save you a lot of the kinds of algebraic manipulations that you might encounter in some of those courses that I mentioned. I'm going to declare a variable t, an independent variable t, and then what I'm also going to do is declare 3 intermediate variables as functions of t. So I'm going to declare that these 3 variables, x, y, and z, are functions. So just like we declare variables like this with the var function, we declare function variables with the function. All right, and what I'm going to do next is I'm going to create an expression R that is that matches the expression over here, x, y, z over this round robin of products. X of t, y of t, z of t, like this, divided by the round robin, so y of t times z of t plus x of t times z of t plus the last one, x of t times y of t. And I'm going to show that to you just so that we can sort of comfortably look at it. So here we see x, y, and z of t in the numerator and xy plus xz plus yz in the denominator. Okay. Now we can ask Sage to differentiate this with respect to t and simplify it a little bit. So I'm going to call that variable dr dt, and I'm going to let it equal the derivative of r with respect to t, like that. And I'll show it to you. And you might think, oh my God, what a disaster. But yeah, I mean, there's a lot going on here. It's a big mess. But we have Sage now at our disposal, and we can use Sage to simplify these nasty expressions. So I'm going to take dr dt, and I'm going to overwrite it with the simplified version of dr dt, which we can get by calling the simplify full function. And then I'll show you the simplified version, dr dt. Not a whole lot better, but not terrible. If you stare at this long enough, you can kind of see some patterns. You see y squared z squared dx dt, x squared z squared dy dt, and x squared y squared dz dt. So there's a kind of pattern there. And then in the denominator, we see a more complicated expression, x squared y squared, and then we get these sort of expressions, x squared 2xy y squared, which you might recognize as simply x plus y quantity squared, z squared, and then other variations of that. Cool. So if you're in a physics class and you're doing sort of an abstract derivation, you might find this SAGE functionality really useful. But we're not done yet. One thing that we know about this expression is that dz dt is 0. So we could incorporate that into our expression, and we could say dr dt dot substitute. I think I've got that right. And we're going to replace the derivative of z of t with respect to t with 0. And we'll see what that looks like. So this is the derivative of z with respect to t, so diff z of t with respect to t. And we want to set that equal to 0. And note the double equal sign here instead of the single equal sign. Oh, and I'm going to show that to you because it's hard to look at these expressions in their ASCII form. All right, we get the same expression back, but look closely at the numerator. Now the term that involves dz dt is gone, and SAGE is smart enough to get rid of that and leave the rest of the expression behind. We can take further advantage of this particular substitute function and actually go through and substitute all of the various pieces that we know. So let's do the complete substitution to finish the exercise. The substitute function is pretty smart. It's able to take a list of things. So let's replace the other variables with what we know them to be. So I'm just going to do a quick copy and paste. Let's put expressions in for x. So what do we know dx dt is at this moment? We know that it's 2. So I'm going to replace dx dt with 2. I'm going to replace dy dt with 1. And we've already replaced dz dt with 0. But we're not done yet. We also have x, y, and z's kicking around, and we need to replace them as well. So we're going to replace x of t. What are we going to replace x, y, and z with? X of t is going to be 100, y of t is going to be 200, z of t is going to be 300. So x of t is 100, y of t 200, z of t 300. Now we can ask SAGE to substitute all that in and give me the final result. And there we have it, 81 1/21, whatever that is. So the rate of change of the resistance with respect to time is 81 121 at this particular moment in time. And what are the units here? They are ohms per minute. Ohms per minute. That's the total resistance. Okay, so a feature of SAGE, little known feature of SAGE, really, really helpful. SAGE can let you declare abstract functions and do integration and differentiation, and it knows all of the things. It knows about the chain rule. It knows about product rule, it knows about quotient rule, and it can do all of these kind of abstract calculations for you and help you check your work in classes where there's more abstract mathematical computation. Like I said, PChem, engineering math, physics, other sort of advanced science classes. Okay, let's wrap this collection of exercises with a multivariable chain rule, a several step chain rule. I'll sketch it out for you, and if I feel like we have enough time, I'll do the whole thing. We have u as a function of x, y, and z. We have x, y, and z each as functions of w and t. We have w as a function of r and s, and t as a function of r and s. And we're asked to find the derivative of u with respect to r. So one end of the chain, the dependent variable u, all the way at the other end of the chain, the independent variable r, and of course s. Let's work this out. We're asked to write an expression using the tree diagram. I've told you I'm not a super huge fan of the tree diagram. I just focus on steps. So I want to find the partial of u with respect to r. I better find the partial of u with respect to each of its independent variables x, y, and z times the derivative of each of those with respect to r. Partial u with respect to y, partial y with respect to r. Finally, partial u with respect to z times partial z with respect to r. Okay, and now I go and I try to fill in these various bits. And I look at x and I see, oh, x doesn't really depend on r. X depends on w and t, which in turn depend on r and s. So I've got to expand each of these using, guess what? A chain rule. So let's do each of those in turn. The partial of x with respect to r is the partial of x, and now you're going to work through the independent variables for x. X with respect to w times w with respect to r plus x with respect to t times t with respect to r. Okay, and we've got to do that for all three of the partial derivatives. So the partial of partial of y with respect to r, partial of y with respect to w, partial of w with respect to r, partial of y with respect to t, partial of t with respect to r. And finally, we need to deal with the partial of z with respect to r, partial of z with respect to w, partial of w with respect to r, partial of z with respect to t, partial of t with respect to r. Where do you go from here? Well, you're going to take each of these expressions and substitute them in for the corresponding partial derivative, and you're going to get, let me count them up here, 1, 2, 3, 4, 5, 6. You're going to get 6 total terms. Is that right? Yeah, that's a lot of terms. And so you could write those out over here, 6 mixed collections of partial derivatives. I'll leave that to you to write out. For suggested exercises here at the end, I want you to pay attention to all of the different kinds of exercises at the end here. When you've worked enough of them to feel comfortable, go ahead and try the web work assessment for Chapter 4, Section 5. Thanks.